Okay, so application. All right, so reminder, your success failure condition. So a binomial model is considered approximately normal when the number of expected successes and expected number of failures, that's a successes and failures are both why am I shaking, at least 10. So NP has to be 10 or higher, and NQ has to be 10 or higher. Okay, so let's move on to the problem. All right, so here we're dealing with, suppose the Red Cross anticipates the need for at least 1,850 units of O negative blood. Okay, and it estimates that it will collect blood from 32,000 donors. How great is the risk that they will fall short of meeting its need? Okay, so this particular problem is a binomial model because we have a number of trials or a number of donors that we're choosing from. And so we need to check our conditions first. So our conditions would definitely be the success failure condition. So conditions. So success failure. Okay, so N is 32,000, P is 0.06, and Q is 0.94. So we have that NP is equal to 32,000 times 0.06, which I do believe was 1920, which is greater than 10. Awesome. NQ, which is 32,000 times 0.94, which now that number I don't remember. Which is, what did I type? Which is 30,080, which is most definitely greater than 10. So because both of those conditions are indeed met, we can proceed with a normal model. So since both conditions are met for success / failure, the binomial model can be considered approximately normal. And so what that means to you is that you can now move forward with doing a normal distribution model with your information. All right, so with every normal model, remember we need our mean and standard deviation. So this is a binomial model, so that's expected value is going to be N times P. And so we actually already calculated that, which is awesome. So that's 1,920 donors. I think I said donors or units. Either one would work. It just depends on the nature of what we're talking about here. Okay, and so then our standard deviation for our variable would be the square root of 32,000 times 0.06 times 0.94. And so that value is 42.48 units. I'll just call them units. Okay, so now we have our info, and now we're going to draw our curve. And we have to make sure you identify your information. Okay, and so we'll call it amount of O negative, what do they call it? Donors / units. Okay. Oh, let's see if I can draw this curve without, I can't. Okay, so we have our normal model. And so what we're trying to figure out is how great is the risk that they will be short of meeting this need. So we're trying to find the probability that X would be less than 1850, so 1,850 units, okay? So that's what we're trying to work out. So that number would be somewhere about right here. So that would be our 1850, and we're trying to find the probability that it's less than that. Okay, run short. All right, so we're gonna turn this into our Z square. Oh my goodness. Our Z, oh my goodness. And so that Z score is approximately negative 1.648. Okay. Oh my goodness, now, look now. And so we're doing our normal CDF. Okay, great, of course I'm gonna run out of room. Okay, so I got it to fit. All right. And so, okay, so here we go. This is our information. Don't forget to label lower bound, upper bound, mean, and standard deviation. Oh, that looks like something else. And so when you calculate that, you get 0.0497. And so to answer the question, the risk that they will fall short of meeting its need is approximately 4.97%. Oh my goodness. Will fall short of, excuse me, sorry. Alrighty. As always, if you have any questions, make sure you write them down in your notes so we can discuss them in class. Thanks for watching.